Okay, so this will be the first of 4 videos on matrix transformations for Math 1410 Linear Algebra for the Spring 2017 semester. Um, the idea here is that we want to sort of think of this matrix multiplication that we've defined, this sort of strange definition for matrix multiplication, and we want to make sense of this definition um, as a function, as a way of turning one vector into another vector. Right? So the idea here is that if I start with the matrix A, right, so A11, A12, down to A1n, and A21, 22, down to A2n, and so on down to A, say, M1, M2, down to A, Mn. Right? So this is an m by n matrix, and x, my column vector, is x1, x2, down to xn. That's an n by 1 matrix. So we know that the sizes here are compatible, right? The n here matches with the n here. These are the right size where we can multiply them. We can do this matrix times column multiplication like we've done now many times when we're doing matrix multiplication. We know how that works. And notice that what we get a new vector, so we get y, right? So y is going to be, y1 down to ym, right? And we want to define y as a times x, right? So if I actually carry out that multiplication, right, I'm going to get a11 times x1 plus a12 times x2, and so on down to a1n times xn, right, and so on all the way down. That's the first entry, all the way down to the last entry, a m1 times x1, a m2 times x2, down to a mn times xn, right? And don't be thrown off by the fact that this matrix on the right is really wide, right? Because we've got a sum. Each entry is a sum. This is a column. This is a column vector. This is an m by 1 column vector, just as this is an m by 1 column vector, right? This is a column. This is a column. Both of these guys are column vectors. It's just that each entry in this column on the right is expressed as a sum. So it takes up a lot of room on the page, right? So one way that you can think about this is one way you might think about it is you can think of this as defining each of the entries in this vector y. You can think of it as defining each of these entries as a function of the entries in the vector x, right? So yi is equal to ai1 x1 down to a-i-n xn. Right, so we can think of this as a sort of linear function of these variables x1 down to xn, right? And so basically you can think of this as you sort of start with n variables, x1 down to xn, and you have sort of m new variables, y1 down to ym, and so you can think of this, if you like, as a function, right? So we get what we get is a function let's call it t. So it's going to go from Rn to Rm, thinking of these as spaces of vectors, and so t of x is equal to a times x, right? This is sort of the many variables analog of a linear function in one variable, right? Think about in one variable you're thinking about something like y equals a times x. That's your sort of, very basic example where, you can think of that number a as like a 1 by 1 matrix, if you like. So basically what we're trying to do here is we're trying to generalize this humble little linear equation here. Notice that I didn't do ax plus b. We're in the context of linear algebra, so remember, we usually in linear algebra we want to preserve the origin. Think about when we talk about subspaces, right? 0 plays an important role, and we want to make sure that if we think of the graph of this thing, that that's something which passes through the origin. Okay. So we have this idea of using matrix multiplication to define a function. By the way, one of the things that we're not going to discuss in these videos, I'm not going to go through the details. There are some details in the textbook if you're interested in. If you want to kind of understand this strange definition for matrix multiplication, one way to understand it is that once you sort of think about defining functions in this way, where you define a new vector as taking an old vector and multiplying by a matrix, if you move on and you think about composition of functions, so doing a times x to get a new vector y, and then if I did b times y, which would be b times a times x, this is sort of like composition of functions. And it turns out that if you take functions of this type and you compose them, you are sort of forced in to the definition of matrix multiplication that we have. Okay, so just to recap, we can do this generally. We think of this as a function, so we think of this t as a function. This is a linear function. So it takes vectors in Rm. So we want to think of these guys here as spaces of vectors. Right, so for every vector in Rn, it multiplies by the matrix A, giving us a vector in Rm. I should be careful here. This should be an M there in that last entry. Okay, so as we said, we can think of this as, if you like, as a function of several variables, or as several functions of several variables, one for each of the y coordinates. Each of the y coordinates is defined as a function of the x coordinates. Okay, so here's a very simple example. We want to use this matrix A to define T from R2 to R2 by T of x equals A times x. So we can play around with that. We can say, okay, so let's just kind of let x equal to x1, x2. What does T of x look like? T of x looks like 2, 3, minus 1, minus 2 times x1, x2. And we can write that as 2x1 minus x2, and then 3x1 minus 2x2. And by the way, notice one of the things we did when we were playing around with subspaces and other examples like that is that we can take something like this and we can decompose it, right? We have a matrix with two variables in there. One of the things we might do is we might say, you know what, let's write this as 2x1 3x1 plus minus x2 minus 2x2. Let's write that as x1 times 2, 3 plus x2 times minus 1 minus 2. And notice that what you have here, this is sort of the first column of A. This guy is the second column of A. This is sort of a general pattern that we're going to see. We talked about this a little bit when we talked about doing matrix multiplication. We talked about doing this matrix times column product. We said there are two ways you can do that, right? You can do it by doing this row times column rule that we always use when we multiply matrices, but we also said that actually when you're dealing with a column, matrix times column, you can think of that product as forming a linear combination of the columns of your matrix A, where the coefficients in that linear combination are the entries in this column vector here, and we see that in this case. And so one of the things that might tell you is that if y is equal to t of x, then y belongs to the span of these two vectors, 2, 3, and minus 1, minus 2, right? Every possible output from this function is a linear combination of those two vectors, right, for some choice of coefficients, x1 and x2. And this will be relevant because one of the questions that you might have to answer if you're dealing with a function like this, one of the related questions is, you know, if I give you y, you might ask, well, can you solve the equation, you know, a times x equals y? Can you solve this for x? And you know, if you can solve it, can you do it uniquely? That's also a related question. So there are a lot of problems like this that you can ask about these matrix transformations, which are related to a lot of problems in linear algebra and to systems of equations that we're going to encounter as we move forward through this material. So you can play around with something like this. You can plug in different values for x1 and x2, and you can see what you get. But one of the things that you will notice is that you always have this pattern that when you calculate the output of a matrix transformation, the output is always given by taking some linear combination of the columns of the matrix that you use to define that matrix transformation. And by the way, in this case, you know, if we wanted to answer this this question in this particular example, the answer to both of those questions is yes. Why is the answer yes? Well, if you look at the two columns of this matrix, those two vectors are not parallel. They're clearly not parallel. They're not scalar multiples of each other. And we know that any two non-zero, non-parallel vectors span a plane. That plane in question in this case is all of R2, right? So the span of those two columns is in fact all of R2, and that means that every single vector y in R2 belongs to that span. So we can find an x so that a times x equals y in each case. And the uniqueness, we'll see later on that the uniqueness follows from the fact that those two vectors are in fact independent. Okay. Now, these sorts of functions that you define using matrices, these are special cases of what are called called linear transformations. Linear transformations are studied in an abstract linear algebra course. In fact, they're kind of the main object of study in an abstract linear algebra course. But if the only vector space you're going to look at is Rn or Rm, then the only linear transformations that you need to look at are matrix transformations. And there are a couple of important properties. So for any matrix transformation, T from Rn to Rm. By the way, this notation, if you've never encountered this notation before, this is just a way of saying that the inputs all come from Rn, and the outputs, they all land in Rm. And so we know that our matrix transformation is going to look like T of x equals a times x, and we know that this a has to be m by n. Now, just working with properties of matrix transformations, you get a few things for free. You get that T of x plus y, okay. Well, by definition, that's a times x plus y. And we know that matrix multiplication is distributive, so I can write this as a times x plus a times y. But if we use our, you know, that's by definition of our matrix transformation. This is T of x plus T of y, okay? And so this tells you that that this plays nice with respect to addition. In fact, it kind of turns one addition into another addition, because this this addition here is addition in Rn, right? X and Y are both vectors in Rn. This addition over here, well, t of x and t of y, those are both vectors in Rm. Okay, so not only does it turn vectors in Rn into vectors in Rm, it also turns the addition in Rn into the corresponding addition in Rm, right? And the same thing is true for scalar multiplication. Okay, if I take any vector x and any scalar c, right, then that's a times c times x. And again, one of the properties for matrix multiplication says you can take that scalar and you can pull it out in front. You can write that as c times ax, which is c times t of x. Right? And again, on the left, the scalar multiplication is taking place in the domain, Rn, and the scalar multiplication on the right is taking place in the codomain in Rm. So this is one of the reasons why linear transformations are important, is that they not only take you from vectors in one space to vectors in another space, but they also kind of match up the addition in one space with the addition in the other space, and the scalar multiplication matches with the scalar multiplication in the other space. And so, you know, some consequences of this are, well, one thing you might note right away, if you set c equal to 0 in the second property, one of the necessary conditions for any linear transformation is that it has to take the 0 vector in Rn to, and maybe put a little n there to say that's a 0 vector in Rn, that has to be transformed to the 0 vector in Rm. And the other thing you might note is that you can consider sort of any linear combination Ax. If you combine 1 and 2, you have A times t of x plus b times t of y. All right, so that's those are the basics for matrix transformations. We'll look at some specific examples in the next video.